Okay, welcome everyone. Today's speaker is Ishan Mishra from Cornell University. Ishan is a graduate student working with Jonathan Nunin and Nicole Lewis. Today he'll talk about providing new constraints on Europa's surface compositions. That sounds exciting. So Ishan, the floor is yours.
Thanks, Serena. Thanks a lot for inviting me to give this talk. As Serena said, I am a graduate student at Cornell University, and I'll be talking about my thesis projects relating to providing new constraints on Europa's surface composition. Next slide. Sorry. Yeah. So the outline of my talk is going to be as follows. I'll first briefly explain the interest in Europa's surface composition. Then I'll talk about methodology for analyzing its spectroscopic data that I have been trying to push forward and developing a framework for it. And then I'll provide some examples of applications from my own work. So why the interest in Europa's surface composition? Well, I'm sure you all might know, Europa is a prime astrobiological target. It has a subsurface ocean of around 100 kilometers beneath a tens of kilometers thick ice shell. And we believe that the ocean is salty, probably in contact with a higher rocky floor. And so it makes it a prime potential biosphere. And its surface is also pretty young, so because of the lack of craters and young geological features. And so we know that there is active exchange of materials between the surface and the ocean. And the picture here is a famous one where you can see that the famous dark regions of Europa, which are thought to be we have strong evidence that they are non-waterized components. Mixture of things coming from the inside and exogenic bombardment. In this sort of high contrast image, you can see that the northern regions are where the water ice is predominantly dominated in the trailing hemisphere of Europa, whereas the non-ice regions are kind of spread out in the equatorial to mid latitudes, but they're also very neatly match the lineae and other features on Europa's surface. So as I've already alluded to, the surface composition of Europa is a window to its ocean's composition. And so that's why we are interested in trying to constrain the surface composition of Europa, because right now the remote sensing is our best tool to understanding this moon. I'm hopeful that in my lifetime we'll see a mission that can go drill through the ice and explore the ocean directly, but that is wishful thinking at this point. And so if you're trying to understand the composition of Europa's surface, we need to understand it in terms of both materials coming from the inside and materials coming from like the Jupiter's magnetosphere. And so the surface emplacement can be in the form of diaperic upwelling, cryovolcanism, or plume activity. We have tentative evidence of plumes on Europa. And in the magnetosphere of Jupiter, you have a lot of stuff that comes from Io, sulfur. It's a prime component. And so that also falls on Europa's surface, primarily on the trailing side, and gives it a lot of its red color. So when we're trying to understand what the surface, the ocean might be made of, we need to understand if we are seeing the exogenic versus endogenic material. And as I've said, like Europa's subsurface ocean, like as is shown in this schematic diagram, is very likely in contact with the subsurface. With the rocky surface. And so just like in Enceladus, where from the plumes we understand that there's evidence for hydrothermal activity, we're expecting something similar to happen in Europa. And so prime conditions for life like Earth to thrive. And so a primer on Europa's surface composition. So it's primarily dominated by, sorry for the small figure, but it's basically showing maps of amorphous and crystalline ice. So the two predominant kinds of water ices that is found in the outer solar system. And Europa is an interesting case because Europa's temperature conditions in most parts would favor crystalline ice, but because of the intense bombardment of charge of energetic particles, the crystallinity is destroyed and it favors amorphization of ice. So there's like a balance of these two factors to first order, and that determines where you're seeing that basically leads to both forms of water ice being present. And so we definitely have a lot of water ice. Then with Galileo specifically, which took a lot of observations of Europa, we have evidence that there are a lot of different kinds of hydrated salts, primarily sulfate salts on Europa surface, and also hydrated sulfuric acid. And so the dominance of sulfur is again like primarily linked to the fact that Io is spewing out a lot of sulfur that gets trapped in Jupiter's magnetosphere and then gets preferentially bombarded on the trailing hemisphere of Europa, where you're seeing most of these sulfur species. And then we have found tentative evidence for oxides like sulfur dioxide, carbon dioxide, hydrogen peroxide, which have implications for the like potential energy supply to the ocean in terms of redox disequilibrium. And then more recently we found evidence for irradiated sodium chloride, and that is very exciting because it correlates with parts of Europa's surface that you would consider geologically younger, so it could potentially be endogenic. And all the data that I showed just now was reflectance spectroscopy data, which has been our primary tool to understand Europa's surface composition. And specifically the 1 to 5 microns region, most of the spacecrafts that have taken data of Europa's surface have an IR spectrometer that spans this region. And it's important because this has it has a lot of fundamental molecular absorptions. And so like even like future missions that are going to go like Jupiter, like JUICE or Europa Clipper also have a spectrometer that spans this region. And I'll go into more about like the value of this wavelength region in terms of organic characterization in later part of the talk. So we do have you do see prominent features, and we have a good idea of like the sort of like the bulk composition of Europa's surface, but it gets complicated due to various factors, such as firstly speed in the wavelength region where most of our good quality data exists, which is like 1 to 2.5 microns, because beyond 2.5 microns, water's inheritance reflectance is low. And so the data that we have is of low SNR, also because it's irradiation damaged because of Jupiter's magnetosphere. And so, when we look at the 1 to 2.5 microns region, a lot of the broad sort of hydrate features can be fit with acid hydrate, or it can be fit with a combination of salts without any water ice. And so there's a lot of degeneracy in what might be present. Then there is the effect of spectral band shifting due to irradiation, which has been observed in lab works. Then another effect that was been recently studied a lot is the development of color centers, as they're called, in salt crystals. So for example, in here it's showing as you bombard sodium chloride on with energetic particles, over time it develops these very prominent features that also result in a visible discoloration. And that is one of these features was basically what was detected on Europa's surface for sodium chloride, to give us a first detection of sodium chloride. And so all of these need to be thought of when you're trying to understand what features you're seeing in a spectroscopic data, and when you're trying to constrain abundances and so on. And speaking of constraining abundances, so once you've detected a species or you have like some guesses or hypothesis of what might be present, you want to go and figure out how much of that species is present, and whether you can also say something about like the average grain size and porosity of the surface that you're observing. And for that, you rely on spectroscopic modeling pretty much. And here I'm just showing that like if you're trying to fit a spectroscopic model to data, abundances of the species are of course important, but the other physical parameters like grain size is also something that you need to take into account because they can alter the spectrum, and so they are degenerate with abundances. So so that again like adds another layer of complication. But what I will be primarily highlighting in this talk is that apart from using a spectroscopic fitting for getting at abundances or getting constraints on abundances and other parameters, they can also be used as a complementary approach to detection itself. Like if you see a feature or if you have guesses on what might be present in the spectrum, you can actually quantify the evidence of each of your candidates using a spectroscopic fitting approach, which I'll illustrate in the later part of the talk.
Excuse me, we have a question from the audience. Todd asked, what's the mechanism that caused the irradiation to change the spectrum?
That's a good question. I don't know many details about the exact process, but I think it's yeah. I don't want to give an incorrect answer, but I think it's like modifying the crystalline structure of the substance in a particular way. For example, in like the case of color, where like new features are appearing, it is due to like electrons really displacing the in a chloride salt, they're displacing the chlorine atoms, and so I would guess something similar is happening for the spectroscopic shifting as well, where it's fundamentally changing the structure or the crystal, and it's causing the sort of energy levels to move. I mean, yeah, that is my very vague guess, but sorry, I cannot provide a very more specific answer. Thank you for the question, though. So to summarize the section quickly, Europa is a prime astrobiological target with a subsurface ocean whose composition can be constrained via the surface composition of Europa. Reflectance spectroscopy has been a primary tool for inferring composition of Europa's surface, and physical models of reflectance can yield abundances and insights into physical parameters like grain size. As we just discussed, physical processes such as particle irradiation and spectrally similar components make the problem of inferring composition accurately challenging. Keeping all of that in mind, I'm now going to talk about like an approach that can help tackle some of these problems, which is based in Bayesian statistics. So the motivation for this, trying to use this methodology, comes from the goal to answer two fundamental questions. Like, can we systematically determine if there is a significant evidence for a given species in the presence of all possible candidates that you might think are present in the in your spectra, and also while also taking into account degeneracies that might occur due to grain size and porosity and other physical factors. And if you find a significant evidence for a species, then can you also constrain its abundance? And very importantly, can you get confidence intervals on these constraints? So a Bayesian inference framework allows you to do this in a neat way. So the idea is at its core very simple, that you're basically fitting a model to a data set, but within a Bayesian framework, you get to explore a high dimensional parameter space, because if you have many parameters, not only just the abundance of the species that you're considering, but also physical parameters, and if you have many species, then it becomes some high dimensional fitting problem. And so to tackle that, an algorithm that uses Bayesian inference can be helpful. And not only that, so like you can, of course, like by exploring that parameter space, you do get constraints on your parameters. But something that I'm going to talk about in more detail is that you can also use a very specific metric that you get from this analysis to compare models. And so you can compare a model that has a species of your interest versus a model that does not have a species of your interest. And then you can use that to assess the evidence for that species. I would like to just like quickly say that the parameter estimation used for with algorithms like MCMC and stuff has been growing in solar system surface spectroscopy over the past 5 years or 10 years or so. I'm just quickly showing examples from like Martian data sets and photometric data of Europa. But the model comparison aspect of it is something that I'm trying to introduce. So let me first quickly go over the model that is at the heart of all of this. And that is the famous Hapki model of surface spectroscopy, where you basically have an analytical approximation of the reflectance of the surface. So this is just a normalization constant, which is like solar radiance. And it is a function of various parameters, like some observational geometry parameters, some like a porosity parameter, multiple scattering parameter. But the heart of it is the single scattering albedo, which basically governs the scattering property of each of the components in your species. So if you have multiple components, then you get an average single scattering albedo, which depends on the cross-sectional area of your species. So that is where your grain size becomes important. And the single scattering albedo of each of the individual species themselves, which is calculated using the optical constants, which you might have heard of. So optical constants are basically the refractive indices of any material. And in our case, so like in any species that you want to include in analysis, you need to have their optical constants. And that is something that fundamentally limits this analysis in certain ways. And it's hopefully the field will move towards more of this lab data being available, which currently is not as the literature is not very rich with, specifically for like Europa specific materials that are very cold, and also like with the specific salts and stuff. It's hopefully we'll have more data sets in the coming years. But coming to the algorithm, I'm going to quickly talk about the Bayes rule that governs this whole thing. We're basically trying to talk about, we're basically trying to calculate the posterior probability of the parameters of your model. So the probability of the parameter given the data, and the whole fitting exercise is basically trying to evaluate this. And via Bayes rule, it breaks down as a product of the likelihood of the data given the model and the prior probability of the model and this normalization constant. Now, when you're doing parameter estimation, this normalization constant is usually not important. But for our purposes of comparing models, it becomes very important because it's directly the probability of the model itself, related to the probability of the model itself. And so basically, like if you're trying to compare two models and you write it down like this and then break it in via Bayes rule, and if you assume that the prior probability of the two models you're comparing is the same, then the probability of the models given the data is basically the ratio of the evidence, as it's called, the evidence of the two models. And so this is at like fundamentally how we compare models, and the bigger this ratio is, the more M1 is preferred over M2 in this case. And then, of course, like once you have your preferred model, you can estimate its parameters. So in our work, we assume a Gaussian function for likelihood, likelihood probability due to Gaussian errors on our data. And then for the prior function, for all parameters, we assume a constant prior. And as I've talked about, the parameters in our fitting exercise is usually abundance and grain size, the main things that we're interested in, but then are other parameters which need to be sort of accounted for, like porosity of the regolith, internal scattering coefficient, and so on. So a quick example for parameter estimation. So imagine that you have a blue, a reflectance data set shown here in blue, and the green model is the best fitting model, or in Bayesian parlay, the maximum likelihood model. And so, and if you imagine we are trying to do a fitting exercise with two parameters of interest, the grain size and the phase angle, which is G. And so what the sampling algorithm is going to do is it's going to try parameter combinations or samples that provide the best fit, or like are good, provide good fits to the data. And so it's basically trying to sample this like high density region of the posterior function. And once it's finished sampling, you get like a 2D, because we have two parameters here, so a two-dimensional distribution of samples, which account for most of the posterior probability. And then you can marginalize it along individual dimensions to get your parameter constraint. So this is fundamentally how the parameter estimation works here. And here I'm just showing a quick example from my one of my first paper, where we took a lab data of crystalline water ice and analyzed it with our framework. And what's interesting here is that we were trying to get at the our parameter of interest was a grain size, but our model had other physical parameters. And for example, we didn't know what the porosity was, so we just let it be a free parameter. We also didn't know what the error on the data was. Like there was an uncertainty on on whether the error was like some multiplicative factor and some an error of some multiplicative factor. And so we also let that be a free parameter. And so accounting for all of these degeneracies, we still got a pretty good constraint on the grain size, and it matched well with what was known of the sample from photographs of what the size might be, around few tens of microns. So it was a good test. Now coming to model comparison, the idea is pretty simple, that you are interested in comparing two models, where one model has your species of interest X, say, and the other model does not have your species X. So you compare how the two models fit the data. And if the evidence for model one, like the evidence, the probability metric that I had shown a few slides ago, if that quantity is higher for model one as compared to model two, then you would say that species X has been detected at some sigma significance. And that detection significance depends on the difference between the evidence for the two models. And if the model 2 is greater than model 1, that is to say that the model without the species of interest does a better job in fitting the data, then you would conclude that, okay, species X is not detected. And an example to illustrate this is basically shown here, where I have taken a data set that has a mixture of olivine, enstatite, and anorthite, 3 common minerals. And so the data set is shown in red here. And the contributions of the 3 species, depending on what their original abundances was, is shown at the bottom. So you can see that not only are olivine and enstatite dominating, but they also have have strong features, whereas anorthite is pretty spectrally featureless. And so when we do the analysis systematically in the following way, where first we try a model that has all the species that we think are present here. and we get some quantity for that evidence, then we systematically knock off one species at a time. So for example, first we will remove olivine and just try to see if the model, if a model with just ensterite and northite works. We see that the evidence comes down drastically. And so that translates to a very strong evidence for the presence of olivine. Similarly, we'll take olivine and northite and knock off ensteritide, and the evidence comes down even more. And that again translates to a very strong evidence for ensteritide. Next, we try a model with olivine and ensteritide, so not taking out anorthite, and see that the evidence comes down, but not that much. But it still translates to a strong detection, but not as strong as the other two cases, because as I already said, like anorthite is spectrally quite neutral. But this framework still manages to give a strong detection for it. And that is because, there is a mild feature here, but it's also taking into account the contribution from anorthite at all wavelengths, because it's not really like a flat line. It has some characteristic continuum. And so that is how it is able to return this strong significance. Okay. So section takeaways are basically that finding a preferred model by comparing Bayesian evidence is useful in quantifying the significance of detection of a given species in spectroscopic data. And once you have your preferred model, you can also get probability distribution of the model parameters, as well as pairwise distributions, which yield insights into degeneracies between parameters. So I should have pointed out, but in this example that I had shown, you're seeing that there are the pairwise distributions are actually, for example, here you can say that the porosity and the grain size in this case are positively correlated, whereas these two parameters are not correlated. So those kinds of insight can also help you understand your model better. Okay. So now moving on to the final section, which is about applications from my own work. So the very first place where I applied this was for analyzing specific observations from Juno of Europa. So in 2019, Juno took some serendipitous observations of Europa. I say serendipitous because Juno has gone there to study Jupiter, not the satellites, but when during like the ideal time, because it has this extreme orbit where it spends a lot of time away from Jupiter to avoid the radiation belts, it was able to see observe the satellites in this polar orbit. And so one such observation was for Jupiter. And here the regions of observations are shown. And these are, as you can see, like they cover big areas, but they also cover, also show the uncertainty. So it's not like we know that from the 81 or 81st orbit, the data came from here, but we don't know exactly, like if there were 20 spectra taken in this observation, we don't know where those 20 spectra come from, because there was, or at least at the time when we were doing this work, there was a huge uncertainty in their exact pixel position. So the observational geometry parameters were basically not constrained. Like we could not tell what was the incidence, emission, and phase angle for most of these observations. And that was something that we need that is a parameter in our modeling work. So that's why we just focused on this small patch here, where we had 4 spectra, all of them had the same observational geometry parameters. So we basically proceeded with the analysis of the mean spectrum from this data set. And the project goals were to constrain abundance and grain size of amorphous and crystalline ice in the region we were observing. So we wanted a simple goal of just trying to figure out the distribution of the two kinds of water ices, because they have both been detected on Europa's surface, but there really has been no work done or before ours where their abundance were trying to be constrained with spectral modeling, because the optical constants for these two different kinds of water ices were recently calculated. So people had not incorporated them into the fitting analysis previously. And we also wanted to compare the intimate versus linear mixing models' ability to fit the data. So what are these two models? So in reflectance spectroscopy of a surface, you can treat the contributions of different components in that might be present on the surface, by which I mean different species, in two ways. So firstly, you can think of them as basically contributing to the total reflectance in a linear way. So basically you're linearly adding their contributions together, their individual reflectance together. And physically that translates to a surface where there might be distinct patches of different materials. So I don't know, like water here, some kind of oxide there, some kind of salt there. And so effectively the total reflectance of that combined area is like a linear sum of the contributions from these individual areas that are independent of each other. So that is a linear mixing model. And intimate model is where basically the regolith is very intimately or homogeneously mixed, and so the total reflectance is a non-linear combination of individual reflectances of individual species. And so we wanted to see which model worked better, because that can provide insight into what is the nature of regolith you're seeing, whether it's linear, whether it's intimate. From previous studies, as I've said, we know that both forms of water ice exist because we see their distinct features. But yeah, in this case, in study, we wanted to get at their abundances. So quickly summarizing the results. So we compared 4 models, one which had both the kinds of water ice for the 2 different mixing schemes, and 2 models which had only one kind of water ice. And in the column here, it's what we're basically showing is the preference of this reference model over these 3 models. So in this case, for example, the intimate mixing model is preferred over the linear mixing model at a very high significance, and the same goes for like these two cases with only one species. And so the intimate mixing model was our preferred solution with a very large amount of amorphous ice and a small amount of crystalline ice. And but when we look at the solution, like if you look at the maximum likelihood solution from an analysis, it's not the best in terms of like it's not fitting certain regions that, and we expect that because we are just using 2 species. We are not, Europa surface has many species. We have not incorporated them into an analysis for simplicity's sake, and also because the optical constants are lacking. But if you just look at the highlighted regions here where the fit is good, we were still finding a discrepancy between the RMS noise that was given to us by the instrument team and the scatter in the residuals in our data. And so this factor is pretty high. And that we took that as an indication for underestimated errors. So basically, the errors on the data set are probably underestimated by the factor of, well, this many. And that's why I redid our analysis where we inflated the error on the data by 20, 30, 50 times to account for that discrepancy shown in the previous slide. And we found that our estimations were pretty robust, and our conclusions about like which model is preferred was pretty robust. Of course, the degree of confidence goes down as you increase the noise in the data, because the algorithm has more difficulty telling models apart if the data is of poor quality, but we're still pretty consistent. And as I said, like, of course, there's indication of missing components, and some hoping that like once we get optical constants of species that like salts and other things that we have evidence for from previous works, if we get the optical constants that span the entire wavelength region here, we can incorporate them and revisit this analysis to probably explain why we are seeing these discrepancies. Okay, moving on to the second project. Here I revisited select Galileo NIM spectra of Europa. So Galileo NIMS has been our like treasure trove for like understanding Europa surface, because it has given us the most amount of data, and the resulting analysis has given us the most sort of comprehensive picture of what Europa surface looks like. What we wanted to do was basically go back and with selected spectra, just do a comprehensive fit modeling analysis. And when I say comprehensive, I mean not just incorporating as many species as we can, but also taking into account uncertainties that might come due to physical parameters like I've talked about grain size, porosity, but in this case, NIMS had a inherent uncertainty of like calibration uncertainty of 10% that most previous works ignored. Or so we wanted to incorporate all of that into analysis so that the final estimates we are getting on the abundance and or like just when we are doing a model comparison, all of those things are taken into account. And yeah, so the species we selected were amorphous ice, crystalline ice, acid hydrate, carbon dioxide, and sulfur dioxide. And of course, one of the main factors that we've selected these 5 species is because they had the optical constants available, but also because it's a nice contrast between the dominant species on Europa surface and 2 trace oxides. So amorphous crystalline ice, as I've said, we have found them very strong features associated with the 2 forms of water ice all across Europa's surface. Acid hydrate is sulfuric acid hydrate, and sulfuric acid hydrate again is thought to be primarily dominating the trailing hemisphere of Europa. So basically this part of Europa, also where our data is coming from. And it's a major product when you do theoretical calculations of sulfur and water ice's reaction in radiolytic reactions. So sulfuric acid comes out as a dominant equilibrium product. And so we expect that to be there. And carbon dioxide and sulfur dioxide are trace oxides that have been seen in these parts of Europa, but we have not found very strong evidence for. So yeah, so that's why we wanted to include them in our analysis. And specifically for the trace oxides, this figure is basically showing the optical constants, so the real and imaginary part of the refractive indices. And you see that carbon dioxide and sulfur dioxide have sharp features. It's just that they're in terms of like the imaginary part of the refractive index, which is a proxy for absorption. But there's order of magnitude difference between their feature strengths and the feature strengths of water ice and acid hydrate, the dominant component. So, but still to be agnostic, include them in the analysis. So a background on the species quickly. So sulfuric acid hydrate, as I've said, is a dominant species in the trailing hemisphere of Europa. We already were expecting it from our like understanding of radiolytic chemistry happening on Europa's surface. But in a 2005 paper, Rob Carlson led an analysis of the trailing hemisphere data of Europa from Galileo using a simple model that had sulfuric acid hydrate and water ice. And it showed that the trailing hemisphere is predominated with acid hydrate, and also that the regions of domination correlated well with the discolored parts of Europa, and so like the parts that are exogenically damaged or radiationally damaged. And so that again, that tied well to where you would expect to find sulfur particles bombarding. So I'm just for reference, our data comes from here. So like one of the data set comes from a region of high discoloration versus the other 2, which are not coming from slightly outside those regions. Carbon dioxide and sulfur dioxide in this work by Hansen and McCord, they were found to be present in certain parts of the trailing hemisphere and the anti-Jovian hemisphere. And the evidence, the feature strengths were weak, but for carbon dioxide, they found that it was probably correlated with some like discolored parts. So, which you could, which if there were strong detections, you would say that they are correlated with like probably endogenic material. But we were just focusing on this one spectrum. So, but still, it overlapped with where carbon dioxide was found in this previous study. Okay, so quickly summarizing the results. So for acid hydrate, we find that it's pretty dominant in all 3 spectrum, which is expected. All of them are coming from the trailing hemisphere, and we find greater than 30 sigma significance for all of them. And in the Bayesian evidence scale, that is pretty strong. And the amount of acid hydrate in S1 spectrum coming from S1 is very high as compared to the other two, or higher. And again, that makes sense because S1 is coming from the most discolored part or most non-water ice dominated part. As for amorphous and crystalline ice, for S1, we get weak to moderate evidence for both forms of water ice. So either of them work well, and that is because the abundance is pretty low, so it can't really tell which of them, if either of them are present. So the only moderate evidence. For S2 and S3, on the other hand, we get very strong evidence for crystalline ice, but a weak evidence for amorphous ice. And we interpret it to be basically showing the difference in irradiation. So S2 and S3 are coming from regions that are not as visibly darker than the region from S1. So they are not as radiation processed. And so water ice has basically not been amorphized to the depth to high depths. And so the region that is being probed by reflectance spectroscopy, which is the very, very top of the surface, still has some crystalline ice presence. And so that's why you're seeing the strong detection for crystalline ice. And in fact, in the data, we do see a 1.65 micron feature of crystalline ice. So we already were expecting that, yeah, this would result in a strong detection. Band shift, I said that in this, the data set, Europan data set does show shifting in bands of water hydrates. And so it's basically so water hydrate bands are getting distorted, and you're seeing that here you see that S1's band is visibly shifted as compared to S2. And so we also had a parameter that would account for that shift, because we didn't want the abundance parameters or the grain size parameter to be unreasonably modified to account for this to shift, to get the fit right in these regions, though I didn't want the model to use the abundance parameter. So we wanted to put another parameter to account for this effect. And we find that the shift is again as expected by eye, and also by where these spectra are coming from. So S1 has a high shift as compared to S2 and S3, where basically we get no visible shifting. And finally, we find no evidence for carbon dioxide and sulfur dioxide in this data set. We were expecting it because, again, previously we have not seen any features, but then you also see that with the NIMS's resolution element, even if you have sharp features in these theoretical spectra that I'm showing here. So in brown, it's a very high amount of carbon dioxide, but what I'm trying to highlight is that even if you have very sharp and strong features, NIMS's resolution element is just too broad to pick that up. And so this was never going to be detected strongly. So the sharp features were never going to be detected strongly, and the effect on the continuum was not significant enough to give any kind of evidence in our analysis. So finally, I'll quickly conclude with my talking about my current project, which is about exploring detectability of organics on Europa's surface. The idea of trying to constrain organics on Europa's surface was to basically try to constrain the organic content of the subsurface ocean, because organic matter is the raw material for life as we know it. And so one of the primary goals for upcoming missions like Europa Clipper and JUICE is to map the organic content on Europa. And specifically, we're interested in finding signatures of organic in the fresh material that might be present on Europa's surface, fresh plume deposits or volcanic deposit, and so on. So the project goals here are to determine observational requirements that will enable detection and characterization of specific organic species on the surface of Europa and in general icy moons through spectroscopy, and with a special focus on Europa Clipper, because I'm part of the collaboration, and also because it's going to be give us the best data set with the best chance of doing this. And then also in the process, get started with an established data analysis and interpretation framework, with which we can systematically identify a class of organic or a particular organic species in low SNR and spectrally complex regimes. So more details about this in the coming slides. So the near infrared region, I have already talked about it, but specifically the 3 to 5 microns region has long been held as like a very promising parameter space for finding organic signatures, because as you see in this set of simulated spectra, even for simple organics that I've shown here, the spectra are pretty rich in features as compared to water ice, which is pretty spectrally neutral. So in a background that is primarily of water ice, you expect organics to stand out. Of course, like the problem is complicated by the fact that we expect organics to be present in very low amounts, given what we know from Enceladus's ocean's organic content that we have measured in the plumes, our own oceans, that organics are going to be present in trace amounts. And so if you actually model spectra, as I'm done in this middle panel with water, ice, and a specific hydrocarbon or organic, I think this is like 5% abundance. Their features are pretty much like tiny dips on a water continuum. And if you zoom in, so here's basically what you're seeing, the level scale of the features, few percent reflectance at most. And so we want to see how does this compare with our expected performance of the upcoming instruments. So I start with the simple case of hydrogen cyanide, because simple molecule, sharp features, and we have seen tentative evidence of cyanide bond on Callisto and Ganymede. So it's a good place to start. In the figure here, it's shown that I'm showing basically like how the features change with increasing hydrogen cyanide abundance. It's unrealistically high abundance, but it's just highlighting the fact that the features do get very strong and are very sharp. So what I have done in this preliminary study is that I basically am interested in this metric that I'm defining called, which I call average feature strength, and it's a proxy for the significance of detection. So basically it is calculating how strongly do these features stand out with respect to the background noise. So for every organic, I can select 2 or 3 features that are sharp, and I'm just going to calculate how strong are they as compared to the background noise, and use that to estimate like, okay, I'm confident of my detection at certain significance level. And so you do that for varying amounts of hydrogen cyanide, or varying amount of your trace species of interest, in this case hydrogen cyanide, and for varying amount of SNR data, and you can get this heat map. So on the left-hand side, I'm showing an example case for like a simulated data set with 50% hydrogen cyanide, 50 SNR and 10% hydrogen cyanide. And you can see that the 2 strong features that I am using for this calculation are present here. And then you use that and the background noise to estimate the significance, get the point on this heat map. And so I'm also mapped the estimated SNR for Clippers, Europa Clippers spectrograph, which is called MICE, Mapping and Imaging Spectrograph for Europa. And these limits is basically like the mission requirement, but current estimates are about like we can get data up to 100 SNR in the 3 to 5 microns region, which is pretty good because it's a very low reflectance regime. As you can see, it's just a few percent reflectance. And here I'm also showing previous and like rough estimates for the ability of previous and current facilities. And that includes ground-based observatories and Galileo and Cassini and all these spacecrafts. And I mean, they have been scaled to the same sort of spatial resolution as Clipper MICE. So basically, imagine both like Clipper observing a 10-kilometer pixel on Europa surface, and these other facilities observing the same patch, and then what would the data quality from that patch look like? That is what I'm comparing here, because Clipper is going to map most of the Europa at a 10-kilometer resolution. So so the 3 sigma contour and 6 sigma detection contours are shown here. And so if we are counting for like counting on Europa Clipper giving us 100 SNR data, then you can expect a few percent of hydrogen cyanide to be detected. And that is definitely at the higher end of what you might expect in terms of organic content. And so that's why I'm trying to now, so that like when you see like tentative features for a particular organic, and if you use the Bayesian evidence approach that I have highlighted, or like that uses spectroscopic fitting, it can actually give you stronger detection. It complements the just seeing the features, but it also gives you a stronger detection metric. As you can see here, like the 3 sigma and 6 sigma contours have been pushed down to lower percentages. And that is primarily because it's not only taking into account the tiny features of these organics, but also their effect on the continuum, because that it matters when you're trying to detect something which is the signatures might be so weak. So in this example, I'm showing like if you look at the best fit model that comes from best fit solution that comes from a model without hydrogen cyanide, this orange line, it basically misses the continuum of the data set, because the data set has hydrogen cyanide. Even if it is very low, it does affect the continuum. So that is the important point. So hence it is a good complement to looking at the features and then going after or trying to quantify the evidence of what you might think is present. All right. And yeah, so hopefully like I've just started with this work, but in this problem is challenging in terms of the spectral complexity of organics. And so something like this can be helpful. So in this ongoing work, I am going to next add other trace species like carbon dioxide, hydrogen peroxide, and sulfur dioxide, which also have features in the 3 to 5 microns region, and we have tentatively detected them on Europa. So their features can overlap with some organics. So I want to see how that affects our ability to infer detection. Tests with multiple organics mixed together, because organics themselves have overlapping features. Test sensitivity of detection to observational geometric parameters and parameters like regolith porosity and grain size, because they do affect the spectrum. Although in a low reflectance regime, I'm expecting them to not matter that much. And also because organics have sharp features, and so these things will not affect sharp features. They affect mostly the overall reflectance level. And add a JWST near spec estimate. So JWST's near infrared spectrometer has a guaranteed time observing program to map the surface of Europa and Enceladus. And it is going to cover this 3 to 5 micron region. So I do want to do some calculation for estimating SNR from those observation sets and seeing if how they line up with the heat maps that I've shown. Okay, so takeaways from my 3 projects that I've shown here. So in the first project, I analyzed a set of stacked Juno spectra of Europa, and which showed high concentration of amorphous size along with a preference for intimately mixed regolith. In the second project, we analyzed 3 Galileo spectra of trailing hemisphere of Europa, and they showed high dominance of sulfuric acid consistent with exogenic sulfur bombardment patterns. It was the first analysis to have included carbon dioxide and sulfur dioxide in it to try to constrain their abundance, but we found no evidence for them. And in the current project, I am trying to establish the detectability of organics in a background of water ice. And it shows that Europa Clipper should be able to pick up signals at a few percentage abundance limits, and a complementary detection method using Bayesian evidence can help push the limit down to a fraction of %, hopefully. And so, yeah, keep an eye out for that paper that should come out within the next few months. Okay, so to conclude, interesting observations coming up from James Webb, Clipper, JUICE, hopefully a lander that can give us like real, more sort of multi-pronged analysis of the spectrum we are seeing in terms of looking at it and also doing spectroscopic analysis and other kinds of analysis. But for now, Clipper is definitely going to bring the next revolution in what we know of Europa surface. And so personally, and like as I see the field going forward, I think it's very important to develop analysis tools, as I've talked about, but also perform laboratory work, because they not only support the models that I'm using and other people use, but they also you can also use lab data to test your models, which is something that has not been done much, specifically for Europa like case, where your actual sample might be damaged by radiation and your chemistry is modified by radiation. So your ocean's composition is not very directly reflected on the surface composition. So we need to do lab work where we irradiate samples, we take the spectra, and then we test our models on those spectra to see where we are lacking and then modify the models, because currently the model I'm using doesn't incorporate irradiation effects and stuff. I can use empirical parameters, but a more detailed study needs to be done. So that is where what I want to do and what I feel like the field is moving towards. And beyond Europa, just want to quickly highlight that I have also worked on analyzing some doing some exoplanet-related work, because one of my co-advisors is Nicole Lewis, is an exoplanet atmospheres person, and so I have supported a lot of transmission data analysis. And currently, I'm working on a project about characterizing exoplanet surfaces with James Webb Space Telescope, where we are simulating mineral spectra with JWST's mid-infrared spectrometer. And for a shameless advertisement, I am on the job market. But again, like if any of this interests you, I would be very happy to talk and discuss any kind of potential collaboration. So thank you a lot for listening. I'm sorry if I ran over the time, but yeah, I'll be happy to take questions. Thank you.
Thank you, Ishan. It's a very interesting talk. And do we have any questions? We got one question from Todd.
Yes, thank you for a wonderful talk. An awful lot there to unwind. I have maybe a set of intertwined questions to ask. I guess there's two main things. One is I'm curious of your ability to potentially date the age of Europa's surface. That is, presumably it takes a while to establish that trailing hemisphere pattern. Mm-hmm. And related to that, while your work on organics sounds absolutely fascinating, if I posed maybe a different question, is there a frank geologic or frank signature of endogenesis? I guess you're saying that something has erupted recently and put some junk on the surface. And what would that be? What would you look for to try to find that? So that's the age and evidence, geologic rather than biologic evidence for recent emplacement on the surface.
Yeah. Okay. So, I as I've said, like I have tentative evidence for plumes. So plumes have been detected on Europa with like Hubble Space Telescope. So if we go to Europa Clipper and we find plumes, then you would go and look for deposits of that plume, just like we did for Enceladus. And then that would be like the freshest material that you could ask for. And because Europa Clipper plans to like go and study those, so like that depends on sort of like finding the plumes that are active when you go. But also the other thing that they're planning to do is to look for hotspots. And since we know that a lot of these as I showed in, like as you see in Europa's surface, a lot of the cracks and the tectonic, the surface features sort of map very well with the dark colors. So that sort of is taken as an indication that it might be like due to salts coming out from that surface. So from the subsurface ocean. So that is definitely something that we want to analyze more closely. But like, I mean, that was probably going to be like those deposits are probably much older than anything you will see via like plume deposits. And so then it becomes a matter of understanding, okay, if something has come out and it's been there for a long time, then what happens under radiolysis? Like, how does it reach this equilibrium state of where you're seeing these particular salts? Because there's something coming from inside, particles bombarding from outside, and so what is the equilibrium state composition? And yeah, I guess once we get there and once we find these species, and if we are finding things that are distinctly correlated with these regions of with these regions of the lineae or the cracks that I've been talking about, or even the chaos regions, which are these regions on Europa where basically it's seen as like the surface kind of like just collapsing, and it's also seen thought of as like the more younger parts of Europa. And so so I guess like yes, it would be interesting if we definitely see a like distinction between the composition and how it relates to geology. And then of course, like I think the plume deposits are the best way to get at the current composition on Europa's ocean, because the problem just gets very complicated if you let things sit on Europa's surface for a long time, because irradiation changes a lot of things. So yeah.
I guess though my question is a little bit different than
I'm sorry if I misunderstood
than what you answered. So looking for plumes, fantastic. Looking for an infrared hotspot, great. That's exactly what you want to do. But you're looking at chemistry.
Yes.
And so I'm asking you, as it were, to predict before I can see a plume, before I can find the hotspot. You would say, oh, you see this species that can only have come up from the ocean underneath. It cannot be placed exogenically. Right.
Yeah. Okay. Now I get it. I'm sorry. I misunderstood your question. Okay. For that, I guess, I mean, from the top of my head, I think the crystallinity of water ice is something that people are definitely thinking of as an indicator for the freshness of materials. For example, because the longer something stays on Europa's surface, especially near the equators where the irradiation is quite high, you would lose the crystalline nature. And so if you're finding something which is very predominantly crystallized and less so of amorphous ice, then that could be an indicator that the material is more pristine. But so that would be my guess for how a composition can provide some idea about the age of the material you are seeing. I can't think of something else that would be definite. Because I think everything is probably a mixture of exterior and interior exogenic materials.
Thank you.
I hope that answers something.
Yeah, that's.
Yeah.
Okay, thank you for the question and answer. And we are kind of out of time. So let's thank you, Ishan, again for the wonderful talk, and see everyone next week.
Thanks a lot. Bye-bye.